All right, good morning, everybody. So that's the second lecture by Sally. She wrote complaint suggestions to this email. It's not only for complaints and suggestions. If you wanted to say thank you, you could also send a message there. Okay.
Thank you.
Thank you. Yours.
Okay. So I really meant it that I do very much appreciate suggestions for things that are not clear that I say. Also, if I make any mistakes, I appreciate that too. But do communicate, because I like to hear from people to know if it's the right level, the wrong level, whatever. So today I'm going to continue my introduction to Smith. Yesterday I introduced this very generically. Today will continue to be generic. And I hope what you're going to get from this is an idea of what the standard model effective field theory does for you and what all the kind of pitfalls and sausage making that goes into this completely general theory. Okay. So it's not really completely general. So yesterday I ended by talking about gluons going to Higgs. And I talked about gluons going to Higgs basically because that's something that I work in. But everything I say about the standard model effective field theory, you could take your favorite process. These are all very general things that happen in all processes, essentially. So I talked about how the standard, is that me stepping on the snakes, I think?
No, that's good. It's just we're checking the out.
All right. Okay. So the standard model effective field theory, as I said, is an expansion in higher dimension operators, where the first set of operators is dimension 6. So the first set of terms is suppressed by this power 1 over lambda squared. And I talked about examples yesterday where the thing that gave you the dimensionless variable was v squared upstairs, where v is 246 GeV. But there are also operators in the standard model effective field theory with derivatives. And the operators with derivatives give you, instead of v squared upstairs, they give you factors of energy squared or PT squared or something, which depends on the kinematics. So here's a very, very simple example of how these things go. Suppose I'm looking for a Higgs boson, but now I'm going to look for a Higgs boson plus a gluon. So a Higgs plus a jet. So this is a two-body initial state, two-body final state process. So the final state has transverse momentum. There's an energy kinematic dependence on the transverse momentum of the gluon or the Higgs. So if I plot the transverse momentum spectrum of the Higgs here as a function of the transverse momentum here, notice that this scale is completely ridiculous. It goes over many orders of magnitude. And you're certainly not measuring it over this many orders of magnitude. And the black here is my standard model prediction. So I just calculate in QCD what I would expect to make a Higgs plus a gluon. Straightforward calculation. But then I put in the standard model effective field theory, and I put in some dimension 6 operators. And what happens is you can get curves. Here's the blue curve, here's the red curve. And these show putting in some new standard model effective field theory operators with coefficients that are constrained so that the overall rate for Higgs production comes out right. So this blue curve, the red curve are allowed by data. And what you see is that as you go to high transverse momentum, these things are becoming larger, and you can get effects here that vary from the standard model by an order of magnitude. So this, yes. The transverse momentum of the Higgs, say. So the two gluons are in the initial state, and the Higgs is made of transverse momentum relative to the initial state. So it's nothing sophisticated. Yeah. So you can worry about what's happening here because you can get very large effects in the tails of the distributions. So this is a conundrum that you always get in this effective field theory business. So when you get large effects, then you start to worry about whether the theory is consistent, right? You're getting effects of order of magnitude here. So you have to find some sweet spot in here where you have an effect that you can measure, but you still think that the theory makes sense. So. Okay. The other thing I emphasized yesterday is that when you do these things, you can't measure just one process. You can't do an experiment, measure, say, the PT spectrum of the Higgs and say, aha, I'm going to measure these effective field theory coefficients. You have to measure a whole lot of processes and put them together. I showed you yesterday that if you measure, say, just Higgs production, it depends on a couple different coefficients, which could just cancel each other. So if you want to separate out these different effective field theory coefficients, you need to measure a bunch of different processes. And in this particular example, you can measure, say, Higgs production. And then if you measure CTEQ, so these things are top quarks, you can measure the red blob. I always use to mean a non-standard interaction. So it's a standard model effective field theory interaction. So you put the two processes together. So here's one of the processes, the green is another one, and then you pick out by the overlap to actually measure these coefficients. And they all work exactly the same way. To measure coefficients, you put together a bunch of processes. Okay, so how do we learn from this standard model effective field theory? So what we need our precise experimental measurements. We need our precise theory. So we need the standard model to next leading order is the standard in high energy theory. And then you need the standard model effective field theory contributions. And you need these also very precisely in order to learn something. So what you really want, I said LHC here, but it's any collider. You want your data to be very precise. You want your prediction to be very precise, and you want to see some effect in the tail from these PT squared over lambda squared effects, where these error bars from the data and the theory are precise enough that you can distinguish them. What you don't want is something like this. So it's all about the uncertainties. Okay. So is this whole thing useful or necessary? I argued yesterday that if you want to look for some new high scale physics where you don't see some new particle, that this effective field theory approach is the only way you know how to go at it consistently, that you can't just put in phenomenological fudge factors to do this. And here's an example of how this works. Suppose I look for Higgs decaying to BB bar, very simple process, and I calculate this decay width in the SMEF. Okay, so this thing is in the SMEF, should have a subscript maybe, normalized to the standard model. So I'll parameterize it as 1, that's my first term, and then some delta kappa here. And this delta kappa, I can write in terms of all of these effective field theory coefficients here. If you can look up what they are, they're kind of irrelevant. There's terms that come from normalizing the Higgs kinetic energy. There are terms that come from the relationship between the Fermi constant and V. There's some new dimension 6 operator. But the point is, these are just coefficients. So you might say, well, you're making it too hard. This just looks like a fancy way of having some fudge factor here, and you just described it in some weird way. And that's absolutely true for this particular example. And let me point out here, I put the link here. If you ever want to do any of this stuff, you can get the Feynman rules from this reference, and they also have UFO files and so forth. So you can feed your Feynman rules into FineCalc, FineArts, whatever packages you use to do things. So it's all automated. Questions? Okay. So that example was too simple. So let's think about another example. We'll think about Higgs goes to 2 Z's. So now you guys all know that the Higgs boson weighs 125 GeV. And you know that the Z mass weighs 90, give or take. So when I write this, you can't have a Higgs decaying to 2 Z's. What I really mean is that the Higgs is decaying to 1 on shell Z and the other Z is decaying to 2 fermions. So high energy physicists always write it this way just because we're lazy. So when you read H to Z, Z, you really should read this. Okay. So I can do the same thing. I can calculate the decay width to Z's plus 2 fermions in this effective field theory and in the standard model effective field theory. And there are 2 kinds of contributions. So it's 1, and then my expansion 1 over lambda squared, just like before. So there's a combination of these EFT coefficients, and I just wrote it here. And in point of fact, that's exactly the same combination as on the previous page. So this is just, some combination of things. But then there's another piece here, which depends on other operators, but these are derivative operators here. And these derivative operators mean that this coefficient here depends on the kinematics of the process. It depends on the cut you put in it and so forth. So this thing is not just an overall factor, but actually has information encoded about the experiment. So it's no longer just multiplying what you had before by some fudge factor, but you're encoding the kinematics. So the effective field theory has more information than the total rate. And this is true for every process, that you don't just measure the total rate and look at how it scales, but by measuring these distributions, you're seeing these PT squared over lambda squared effects or information about the kinematics. So for example, in this process, if I look at the two fermions, their invariant mass to be Q squared. So then the distribution of the width with respect to Q squared is a standard model rate, some overall scaling, which is boring, but then a piece which depends on Q squared. So now in this effective field theory language, I can learn something from the distribution. So it depends on the Q squared. So this kappa formalism that I talked about yesterday, where we just look for rescalings of things, doesn't capture this momentum dependence here. Okay. So I'm going to show you a lot of plots from SNOMAS. And you'll see that the SNOMAS plots actually try to rescale the HCZ coupling. Yes.
Sorry, on the last slide, we had this Q cut. That is another scale that we introduced.
That's an experimental thing.
Okay.
That when they're looking for, thank you for asking me. It's always good to slow me down. When they're looking at this invariant mass pair, they put a cut on the Q squared that they can measure. So it depends on the experiment. It's not a theory parameter.
It's not like the
It's not.
say
No.
something from this scale we expect.
It says in this experiment, this is how they do the measurement.
Okay.
They put this cut in. And do I have, yeah, okay, so the cut in this particular plot goes from 5 to 30. And I think at the LAC, the cut is about 20 or 25. So you'll see a lot of tables which have rescalings of the HCZ coupling. And your first thought is, that must be wrong. She just told me you can't just rescale the couplings. You got all these kinematic effects. And so there's actually a swindle that the theorists play on you. And what they do is they calculate the width. And again, this is Z goes to 2 fermions. I'm just lazy here. So they normalize the width to the standard model width. And then they just take it as to be a delta G HCZ. So they've hidden all the kinematic dependence into this thing. So it hides the SMEF complications, but they haven't gone away. So they're just calculating in terms of all these operators, the dependencies of the experiment, and they just shove them in this factor. Okay, so I'm going to show you 2 plots from SNOMAS. And I'll tell you what you're supposed to learn from these 2 plots here. So at SNOMAS, or the SNOMAS process, which took forever, we made lots of studies about how well future colliders could do for measuring these couplings. So this percentage measurement in these couplings, and you'll see, for example, here is HCZ and HWW, which is, as I said, it's not really a coupling, but it's the square root of the decay widths. And the gray here is the LHC projections. So the LHC is going to run to 2042. So this is what you expect to get 19 years from now. Okay, these grays. And then these different colors are different projections from various future colliders, E plus, E minus machines, and so forth. And you see that you improve by about a factor of 2 from the LHC. If you stare at this, people will say, well, this doesn't make any sense. All these future colliders have the same energy and they get different projections. And that's an interesting sociological fact about SNOMAS, is that the different proponents of the colliders told us how long they were going to run. And so if you run 4 times as long, you get a better answer as somebody else running less. So this plot just encodes what the experimentalists told us. So, okay, so this only includes Higgs data. If you stare at this, you can think that you're going to learn something from these machines. But now I'm telling you that if I use the effective field theory, it's much, much, much more powerful. So what you want to do in your studies of anything is you want to take not just this, but you want to take electroweak precision observables. And when I say electroweak precision observables, what I really mean are Z-pole observables, because you all remember that if you E plus E minus goes to Z, the old LEP experiments, the cross-section on the resonance is enhanced by a factor of about 5,000 relative to off the resonance. So these old results are very, very powerful and precise. We'll also want to include, say, W plus W minus production, so forth and so on from both the Tevatron and the LHC, and you top pork production. You put all these into this Smith sausage maker. And I put this plot up here because to me, this plot is an example to young people of how not to make a plot. I mean, I'm serious about this. You should look at this and say, what are they trying to tell me here? This is just like, got so much information, but you know, it's a terrible way to make a plot. Okay, so what are you supposed to learn from this? And why did I show you this? Well, if you have enough energy, you can look at these projections and then go back to the slide before, which just had Higgs, and see that putting in all this extra data gives you better measurements. And you do better in different cases by, you know, sometimes factor of 2, sometimes a factor of 5, but you do much, much better. So you can also see, if you stare at it long enough, that they do dark shaded, light shaded. If you're colorblind, you're screwed. Sorry, you just can't see this. I can barely see this staring at this. So they've got dark shaded, light shaded, and those are different approximations about whether you have new light physics or not. So, and you can see dark shaded, light shaded, dark shaded, light shaded. The assumptions make a huge difference here. Okay. And what else do you see from this? You see that you can measure the muon coupling very precisely at a muon collider. You know, you can see Z and W couplings you can measure pretty precisely at future colliders. And now notice that this is now a log scale here. So by putting in these extra measurements, you actually do much better. So Smith really buys you something here. But nonetheless, don't make plots like that. Figure out another way. Okay, so let's go back to generalizations about calculating in the standard model effective field theory. This theory is renormalizable order by order in this 1 over lambda squared expansion. That means I can calculate loops and I can systematically improve my calculations in any process. So all of these coefficient functions are normalized at some scale. So these coefficients of my effective Lagrangian are defined at some scale when I started to scale lambda, where I've defined my effective field theory. So if I want to calculate something, say at the W mass, the Z mass, I can renormalization group scale them down to my effective energy scale and get logarithms, say, of lambda over MW, because I'm going from where I defined them at the high scale to where my measurements are. So when I start calculating, as I mentioned yesterday, all these tree level relationships that you know and love in the standard model. For example, in the standard model, you know that the W mass is a weak coupling times this VEV over 2. Very simple relationship. But when I start doing effective field theory, I get corrections to every one of these relationships. But of course, that's easy. I just look up what they are, put them in there. I do my renormalization and I get terms that depend on 1 over lambda squared. So in the standard model, we've got the Fermi constant is 1 over square root of 2 V squared. And that's how I get that V is 246. But in the standard model effective field theory, I get corrections. So what happens in the whole physics beyond this is that I start improving my field theory by calculating loops and so forth. And when I calculate these loops, I get a dependence on operators that didn't contribute at tree level. So at loop level, I get a dependence on many, many operators. So I get more and more sensitivity to this big picture. Okay, is that questions? Okay, so for example, I'm just going to show you one loop level result just to show you how it goes. They all look the same. So if I calculate the ratio of Higgs to 2 photons in the standard model effective field theory, normalized to the standard model rate, it's 1. And then you've got some coefficients that come in at tree level. So notice it's minus 40, minus 13, 22. So you get fairly large effects from these kinds of things. And they can have opposite signs. You could absolutely have situations where they cancel each other. And this happens in everything you calculate. And then you've got contributions from other coefficients. These coefficients are limited from W plus W minus production. You've got things that come from G Fermi down here, and then you've got some new contributions. So in this particular example, at tree level, it depended on 1, 2, 3 coefficients. Now at loop level, it depends on however many there are. There are, let's see, 9, 11 coefficients. So you start being very sensitive to new coefficients. So when you do a global fit to all the data you have, you fit all of these things from different sources. Okay. So I can rewrite this whole framework in a more standard or more usual framework. I can write the couplings between Z's and fermions in terms of just some new coefficients. So if I have the coupling between a Z and say 2 up quarks here, in the standard model, we'll call it GL. We know what it is, we look it up. And then we get a new contribution from our effective field theory coefficients. So I can write my Lagrangian for Z couplings, left-handed couplings to the up, left-handed couplings to the down, right-handed couplings to the neutrino, left-handed couplings to the W, so forth and so on. So if you like, you can go back to your familiar language, parameterize the Z, W fermion couplings just in terms of these effective couplings, and then you can look at a dictionary for what these guys are in the standard model effective field theory. And I just wrote it down here just to show you there's a dictionary. So I write the Z TT bar couplings, and then the change is just the change coming from these effective couplings. Okay. Let's see here. Okay, so we can do the fits to all of this stuff. We can do the fits to the Z-pole observables because, as I said, they're very, very precisely measured. And we can see that, for example, the tree level expressions depend on 10 coefficients, of which only 8 combinations appear. So then we get 2 blind directions. This is exactly the same as when I talked about blue goes to Higgs, where there's a blind direction, only a certain combination. It's the same thing here. So you need all of these measurements to resolve these things. And I think the current status for the global fits has like 200 different data points in. So the fits are straightforward. There's nothing sophisticated about them. We simply calculate some observable in the standard model, and we add the Smith fit to it. We do a chi-squared fit to the data. So what happens, for example, this is just like when I showed you what Higgs to gamma gamma. So here's the contribution, say, to MW. So MW, which is predicted in this theory, has whatever we predict in the standard model. Then it has contributions from coefficients. And again, what you should note, minus plus, we don't know what these guys are. The coefficients are all about the same size. So you can have these very, very strong cancellations. Okay. So again, we can look at some fits here. These are fits at LEP, which is the orange, and these are future colliders. Now to the coefficients. I showed you previously Higgs couplings, but now I'll just show you fits to these various coefficients. And you can see that, let's see, this is a log plot. So you increase by, an order of magnitude when you do these fits at future colliders. And isn't anybody going to ask me who cares? Because that's a really important question, which I'll get to later. But what you should be thinking of is, snore. Okay, you're fitting to a bunch of coefficients. You got, 60 coefficients. You're being theoretically rigorous and so forth, calculating all this stuff. But you should really have in the back of your mind, well, who cares? I don't know what they are. Okay. So here's the meat of the new stuff for today. And I want to pause on this slide quite a bit. So this is a really old story, started in the 80s, and it's really deep, and it's at the bottom of the standard model effective field theory. So suppose I'm looking at QQ bar goes to a Z, goes to W plus W minus, QQ bar goes to a photon, goes to W plus W minus, and here's Q goes to a W and then Q prime, so it's up, down, U bar, say, whatever. This same argument works if these are electrons. E plus Z minus goes to Z, goes to W plus W minus. And these red blobs are the interactions, the coefficients. So I wrote down on my slide that they say the QQ bar Z coupling, it can be the standard model piece plus a new piece, which is the Smith piece. Okay, over here, the QQ prime W can be the standard model plus some newtons. So that's what these red blobs are. But in the standard model, what happens is that if I calculate QQ bar goes to Z, goes to W plus W minus, it has a term which grows with energy. Then if I calculate, say, this diagram, it's got a term which grows with energy. And when I put these combinations together, these terms which grow with energy exactly cancel. And in fact, even if I include, say, a mass for the quark, the terms proportional to the mass of the quark will cancel. So they cancel exactly in the standard model. So now you should say, aha, you put in these Smith interactions, I no longer have these cancellations. So no longer do I have cancellations that keep the cross sections from growing with energy because I've spoiled it with these standard model effective field theory coefficients. So here's my question for the day is why is this a really bad thing to do? Anybody know? Yeah, go ahead.
Growth unbounded, can't you just get arbitrarily large cross section?
Yeah, that's part of the answer. But okay, go ahead.
Isn't it a good thing though, if you see it growing, you're like, oh, there's some BSM right there.
Yes, it is good if you see it growing, but the field theory tells us that there's something called unitarity, which comes from the optical theorem, which tells you that cross sections which grow with energy eventually violate the conservation of probability. So just like when I was showing you that PT spectrum, you want to be over here where you think it makes sense, but not over here where you get an order of magnitude effect. Similarly here, if you have a cross section which is growing with energy, it's going to violate this conservation of probability, unitarity. So at some point, it cannot keep going. And this isn't just a theorist talking. This is real world physics. So here I've looked at E plus E minus as opposed to quarks. So here's the neutrino T channel exchange. Here's the photon exchange, and here's the Z exchange. And so this is from what, 40 years ago? So here's what they measured, this cross section here. But if I throw out this diagram, so I throw out the neutrino diagram, I have this blue curve here. So here's my cross section growing with energy. If I throw out this diagram here, then I get this red thing. So you can see that these diagrams are really canceling to make something that's, well, it's not flat, it's logarithmic in energy here. So you see experimentally that these diagrams are canceling. And it should be no surprise to you that by looking at something like this, you can get limits on how much these vertices are allowed to deviate from the standard model. And in fact, those limits are very, very good because this measurement here is very, very good. Yeah, good.
So you can grow as logarithm of energy.
Yeah, log's okay. Yeah, that's okay. But growing like E squared or E to the fourth is not okay. And the reason it can grow with log squared is because you're not actually going to violate unitarity, conservation, or probability till you get way up to the gut scale or something, someplace where we don't know what's going on anyways. So we've seen these cancellations. We've seen them experimentally. So what does that mean for people doing SMEF calculations? You can take the chair, Tim.
Okay, thank you.
I'm yakking. Don't spill my coffee though. Okay, so
Try not.
let me try to do this now for QQ bar, it goes to W pairs. And now I put my red blobs in for the standard model effective field theory. But again, the operators that contribute here also contribute to Higgs production. So I can't fit just one process. I have to fit both of them. Okay, so how do I do these fits? And this leads to a question yesterday about, does this actually make any sense? Because there's a problem here when I actually try to sit down and do this. And what is the problem? The problem is that I've got a Lagrangian, I've got an expansion in dimension 6 operators 1 over lambda squared, dimension 8 operators 1 over lambda to the 4th. Now I want to actually calculate something. So I calculate the amplitude squared, which is going to turn into my cross section. So it could be the standard model piece plus something that's coming from these dimension 6 pieces plus the rest of it. And I'm going to square it. So I've got my standard model result because the effective field theory is always an expansion around the standard model. I've got the interference of the standard model with my dimension 6. That's over here. And then I'll have this dimension 6 squared piece. And I'll forget about these. Okay, so that sounds good. So I'm expanding in 1 over my mass squared, 1 over lambda squared. So I'll just keep these first 2 terms, standard model squared plus my 1 over lambda squared piece. But I instantly run into problems because I'm not calculating, as in quantum field theory, an amplitude squared. I'm calculating just the interference piece, but not the full term. So when I do this, I get negative cross sections. It's super easy. You run your code the first time and you say, I really screwed up this code because you get a negative cross section. And it's generic to this expansion because it's not consistent just to keep this piece because I'm not squaring the whole amplitude. So I get negative cross sections if I do that. Okay, so that's a problem. So then I go back and I say, well, I guess I better keep the absolute value squared here. I better keep this piece here because now it's positive definite because I've just squared a complex number and that's very fine. But if I keep this piece, why don't I keep this piece? And you can see how this argument goes on forever and forever. People standing on their heads. And this is, by the way, is not a solved problem. We don't really understand how this goes. So, okay, so we've got a problem. We're not sure what to do about it, but there's definitely a problem here. Okay, so the first thing you say is, well, maybe this expansion isn't quite right. Maybe I don't really understand this. So maybe, yeah, go ahead. Good, slow me down. Good.
I don't see this equation, how this can be negative.
Because if I calculate this guy plus this guy,
Okay.
I'm not squaring something.
Okay, but if you keep on also a
Standard model and this guy, but it could be negative. The coefficients can drive it negative.
that of course, but if you keep also
If you keep this guy.
Yeah.
Then it's not negative.
and it's
Then it's fine.
Yeah.
But then I say, yeah, so that if I do this, it's positive,
Yeah.
positive definite, absolutely. But this is a term of order 1 over lambda to the 4th. I'm doing an expansion in powers of 1 over lambda squared. So why do I keep this guy, but not the dimension 8 terms, which are the same order in 1 over lambda to the 4th? So yeah, so I solved one problem, but now I have a problem understanding why I stopped the expansion at dimension 6. And as I mentioned, there's a huge number of operators at dimension 8. What did I say? 900 some CP conserving. So you're never going to do a fit to dimension 8 operators. There's just too many of them. But intellectually, you don't understand why you would keep one piece. And you could say, isn't this going to go on forever, this question, right? I do this and then the next order and this and the next order. So you have to think about why these terms might be smaller than these terms. Because otherwise it's not going to make any sense at all. So one way to approach this, not the only way, but one way to approach this is to say, well, if there's actually some sort of coupling that's associated with my expansion. I've got my standard model, and so I'm calculating some electroweak thing in the standard model, and it really has some standard model coupling in front. It's got G Fermi, or it's got something that depends on the weak scale. Okay, so it's got some coupling, and then we'll say, well, maybe my new physics, which I don't know what my new physics is. The whole point of this is to try to learn about this new physics, but maybe my new physics has some coupling too, which I'll call GBSM. So now I just multiply out, just like in the previous page, I've got my standard model. I've got the interference piece here, which now has a standard model coupling and a BSM coupling. And then I've got 2 pieces which go like 1 over lambda to the 4th. One of them is the square of the dimension 6 piece, which is purely BSM, so it's BSM squared. And one of them is the interference of the standard model with the dimension 8 piece, so it's standard model BSM coupling. So you can see that if all these couplings are the same order of magnitude. The dimension 6 squared is the same order of magnitude as the dimension 8. But if we have that the BSM coupling is much, much bigger than the standard model coupling, it would be consistent to keep this piece and drop that piece. So that's some of the logic that goes into your thinking when you do these expansions. Okay, so here's my favorite plot. This plot always gets a lot of attention because it shows a lot of the problems that happen when you try to do this practically. And again, this is for W pair production, but it could be for any process that I do in the standard model effective field theory. They all have exactly the same problem. So what I've calculated is QQ bar goes to W plus W minus. And I've calculated the PT spectrum. So this is the PT of the outgoing W. And this is the differential cross section. And again, notice that this is ridiculous. It goes from 10 to the minus 10 to 1 in picobarns. And this is ridiculous because it goes all the way out to 3 TeV. And I can tell you, we aren't measuring any W's out at 3 TeV. Okay, so the scales are ridiculous, but it illustrates a point. So the black curve here is just my standard model result, just falls just like all curves for 2-to-2 processes do. I guess this is teal. This teal piece has higher order corrections in QCD and electroweave. And you see that they don't do anything here. They're kind of irrelevant. So now I start calculating this thing in the standard model effective field theory. So the first thing I do is I calculate just the 1 over lambda squared piece. So this is a nice expansion. This is the first term in my expansion, 1 over lambda squared. And I'll put in some numbers for these coefficient functions, which I don't know what they are, but I'll put in some numbers which are 100% allowed by all the global fits. So they're not ridiculous, they're allowed. So what happens here? Here's the linear expansion. It goes, and right here, it goes negative. So this is the point that I was advertising before. And so I'm not calculating a number squared, I'm just calculating the interference. It goes negative. It happens in all these plots, and it happens sort of in a reasonable range. So it happens at PT of about a TeV, which is sort of where we think we're going to probe new physics here. So you say, how do I interpret this negative cross section? So there are various approaches in the fits to interpreting this negative cross section. And the one that most people do, they're scanning over all these parameters for these coefficients. They come to a negative cross section, they just throw it out. They keep going. So that is one approach, just to throw out everything where it's negative. Okay. You can say another approach. You can say, well, I know that if my cross section is negative, my expansion is no good, right? Like duh, we know that. So what I'll do is I'll put a cut on my data. I'll say that my effective field theory is only valid up to PT of, take your pick. Let's say it goes negative about 1100. So I'll say it's valid up to 700. I'll put a cut on my data there. Okay. So that makes sense. Anybody want to tell me why that's a problem? Yeah.
But didn't we say that our standard model is valid up to a certain energy scale and then we need the SMEF terms?
No, the standard model can be valid forever.
Oh.
The SMEF is going to probe physics beyond the standard model. Thank you. That's a good question. The standard model, there's no problem. I could have the standard model and it's going to be valid forever. There's nothing new. The reason to use the SMEF is to try to see if there's something new. So no, we don't need a cut for the standard model. This isn't, the answer to this question is an experimental thing, because I've emphasized that this whole approach to learn anything, you have to fit to lots and lots of data. So you go tell your experimental friends that when they're doing all these fits to W pair production, to Higgs production, to top quark production, they got to think of some energy scale and they got to put the same cut in all of their analysis. They'll just laugh at you. They'll say, well, that's not possible because in different processes, there are different energy scales and so forth. So as a practical point of view, that's not going to happen. Okay. So then we say, well, we're just not going to do this. We're going to go back here and we're just going to calculate the cross section squared and the heck with it, because now it's positive definite if I do it that way. So all the fits that you see are not really an expansion in 1 over lambda squared. They're just taking the dimension 6 Lagrangian and squaring it. Okay, so that the assumption that the dimension 8 is irrelevant is baked into all of these plots you see and all these limits you see. They might not tell you that, but it's baked in. So, okay, so we'll do that. Now we've got positive definite things. And these curves over here are what you get when you do that, putting in some values for these coefficients. And again, you can put in whatever you like. They're not ridiculous here. But now you say, aha, well, I get huge effects over here, but clearly that doesn't make sense to get effects of 1, 2, 3 orders of magnitude. The expansion doesn't make any sense. So maybe I'm down here where I get these big effects, but you never quite know where to cut off your theory. You know, you can't have effects that are order of magnitude, but yet you're trying to get limits on these. So different fits have different approaches to dealing with this problem. And it's still an open area of theory is how exactly to do these fits. And to go back to your question, we really don't want to do these. I mean, we really want to find some new particle or something. We don't want to be in the situation that we're in here, where the only way we know to learn about new physics is to do these convoluted effective field theory fits. Okay. So this plot just emphasizes that this beautiful model independent approach, these assumptions start creeping in here. They're creeping in the 1 over lambda squared, the 1 over lambda to the 4th, the QCD corrections. And so if there were no effects from inserting higher order corrections, all of these lines would be just the same. And if there were no effect from going from 1 over lambda squared to 1 over lambda to the 4th, these would all be the same. So you can see that there is an effect here. So people have tried to put cuts on depending on the maximum energy that's available. And as I said, the experimentalists just aren't going to do this in all their fits. But what you can see is that putting cuts on the maximum energy scale to try to avoid these negative cross sections changes everything. So it's a very strong thing to do. These are limits on some effective field theory couplings that affect the Z couplings to fermions. And this is WZ production. And this is a cut on the invariant mass of the outgoing W and Z. And it shows that as I change this cut, as I make it smaller and smaller, I get different limits on these coefficients. So the cuts that I put there are baked into these fits. Okay, so I'm going to show you a couple of the global fits here. You can stare at these. They're not tremendously illuminating, but they do illustrate a few things. So people do these fits to, as I said, sort of 20 operators with maybe a couple hundred data points. So they have enough data points that they can resolve the fact that any individual measurement depends on a lot of these coefficients with pluses and minuses. So they do these fits. Notice, first of all, that this is the minus 100, 100. It's a log scale. These things vary over many orders of magnitude. So the fits, which are orange, okay, are the colors clear in the back? I guess they are. They're orange lines and blue lines. So the orange lines are just a consistent fit to order 1 over lambda squared, just throwing out anything that goes negative. So you don't get such strong fits. You do the fits, including the quadratic terms, the 1 over lambda to the 4th terms, and you start getting big effects. So these are the blue. And it's exactly from that plot I showed you before, where in the tails of the distributions, you're getting big effects. So you can see that going from the 1 over lambda squared to the 1 over lambda to the 4th terms, it changes by several orders of magnitude your fits. So that's baked in here. These particular fits include top port data, Higgs data, W plus W minus production at the LHC. So they include lots of data from many different sources. And you can see that some quantities are limited quite precisely. Here's one, here's another one. And these tend to be quantities that were measured on the Z pole. The other quantities, you know, it's all over the place here. So again, you can generate all this automatically with tools we have just to run the simulation. You can do it with MagGraph essentially. So also another point to emphasize here in all these fits is that I don't probe a scale. My effective Lagrangian depends on coefficients over lambda squared. So the scale I think I'm probing depends on what I think the coupling is, whether I think the coefficients are order 1, order 4 pi, order 1 over 4 pi squared, whatever. I have some idea in my mind about where this stuff is coming from. And so once I have this idea in my mind, I can translate it to a scale. So for example, if you think that the stuff comes from maybe some loop level physics, so maybe these coefficients are 1 over 4 pi squared, then I would be sensitive to a higher scale. So that's the clear boxes here, where this line, you probably can't see the scale, it's roughly 10 TeV. Okay, so if you think that this stuff has very small coefficients, I'm probing the 10 TeV scale right now. Whereas if you think these coefficients are maybe order 1, because I don't know, okay, so I'm sort of probing the 1 TeV scale. So that's how I interpret this kind of data. Okay, questions? Okay, so let me go back now to my question I asked at the beginning is, who cares about all this stuff? I didn't know what these coefficients were when I started. I'm hoping that I measured something that's not 0, because that would tell me that there was some physics beyond the standard model. But after I do that, can I really learn anything? I mean, what am I learning here? Why am I going to all this trouble? This is a boatload of work to put all this stuff together. So here's like the dream, how we think, how a theorist thinks in a perfect world. This might work. So the dream is we do these fits to data. We do them the best way we know how. We put in all of our best theory and our best understanding, and we look at all these pitfalls, get rid of negative cross sections, think about higher order loop corrections. We put it all in, and we measure some non-zero coefficients, and we know that they're non-zero outside of all the uncertainties of doing this fit. And it's all about the uncertainties, because you got to know they're non-zero outside the uncertainties. So maybe in a perfect world, I measure some pattern of coefficients. I measure like 3 non-zero and the rest are 0. And these two are half of each other. There's a pattern. That's the real hope, that I would measure non-zero things after understanding all these uncertainties, and they would have a pattern. So what happens is that then I say, well, if I had a model up at, I don't know, 10 TeV, someplace where I couldn't possibly measure the new particles, I could take this model at 10 TeV, say, I could integrate out the heavy particles from my theory, and then I would match to these coefficients so that in the context of my favorite model, I would predict what the coefficients were at 10 TeV. I would say, these are the non-zero ones, and the rest are 0. And then I would say, I know these coefficients at 10 TeV. I know the renormalization group running of these coefficients, so blah, 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 blah. I chunk down to wherever my experiment was, TeV or wherever. And then I would say, aha, I should have measured this. And so by comparing the measurement of these non-zero coefficients with the expectation from different models, I would learn something about the models. And the patterns of these coefficients are really very, very different in the different models. So people have done this matching exercise for models with extra scalars, with 2 Higgs doublets, for models where you have a vector like top quark, which is a top quark which couples the same to the left and right-handed top couples the same to the weak gauge bosons. So people have done this matching to a lot of different models to see these patterns. And so here's just an example of my dream. Okay, so here is a model which has just one scalar at high energies. And this is a scalar that by assumption has no gauge interaction. So we call it a singlet scalar. And it's a very nice model because in models like this, a scalar can be what we call a portal. It can talk to our standard model world, and it can talk to our dark matter world. So we like this kind of model. So in this kind of theory, you generate just these 2 coefficients, which is not too interesting what they are, okay? So you would generate these correlations between coefficients. So if I had this model, I would generate this green line. So the hope is that you would measure something that sat on this green line, but not sat down here. Okay. So you can do that for different kinds of models and say, aha, I couldn't see this new particle, but because I saw that it sat right here, it might be this model. And I guarantee you, if this ever happens, the model builders will be going to town trying to explain this. Okay. Yeah. I'm an optimist, but in order for that to happen, one of these coefficients here would have to be non-zero. And they're all bang, right on the line. You know, this guy might look a little bit low, but yeah. So we have, that's a great question. We have zero, absolutely no evidence that any of this stuff is non-zero. Yeah. And that's why when I show you that horrible plot with all those colors, we care about that plot because that plot is how we're going to push these error bars down to try to do this pattern. Yeah, unfortunately, it looks like the world is standard model. Let me just say, I could show you a million plots and they all look exactly like the standard model. There's no evidence that there's anything else other than theorists thinking there must be something else. Which is different than experimental evidence. Okay, so you can use this kind of approach to do what's called the Higgs inversion. So the idea is, like I said, maybe you measure that some of these coefficients are non-zero, then you ask the so what question. What does it tell me about anything? So in simple models which have, say, only one new mass of particles, and in models where these one new mass of particles are described in terms of a single interaction, which is a large class of new models, actually, the particles that can contribute to dimension 6 operators have been categorized. So we know all of these 2,499 operators, we know what kind of new physics can generate each of these operators. It's very well known. You just look up in this paper, which has a very nice name, the dictionary. So it's a dictionary. You look up, if I have a new colored triplet, I generate these operators. If I have a new vector triplet, I generate those operators. So I know that, and I know the pattern. So then you can look at the global fit. I showed you all those uninteresting limits on the coefficients, and you can interpret them in terms of these models. And you can say, what do they actually tell me right now? So right now, what they tell you is that, for example, if I have an SU2 triplet gauge boson, which I'll call W1, I know that it's got to be heavier than about 3 TeV. And I know if I have an SU2 triplet scalar, which is one of the things that when people were writing models to try to explain the W mass from CTEQ being a little bit off, they put this guy in and they said, aha, this guy can explain that W mass measurement. And we know, again, that this guy from all these global fits has to be heavier than about 3 TeV. We know that if there's a new Z prime, this guy we'll call a neutral gauge boson, this new Z prime actually has to be heavier than about 8 TeV. So we have limits on stuff that we can't explicitly probe that energy scale, but these limits are coming from this SMEFT approach to new physics. So we have learned something. It's not that we haven't learned anything. It's just that they're all limits instead of observations. So for example, here are new fermions, okay? So this would be a neutrino and a lepton, and a standard model neutrino and a standard model lepton. And we know that their energy scales have to be pretty high for these fits. So this program of physics is continuing and it's very active. And I want to end with a slide about why nuclear physicists might care about this kind of thing. Because of course, I've been talking about high energy physics, but the distinction between high energy physics and nuclear physics is zilch here. It's exactly the same. So at an EIC, you're going to have electrons and quarks go to electrons and quarks. Okay. But if I turn this guy sideways, I would have QQ bar goes to 2 leptons, which is the Drell-Yan process at the LHC. If I turn it sideways that way, I would have the E plus E minus goes to jets, which was measured at LEP years ago. So they're all from a standard model effective field theory point of view, they're the same thing. In the standard model effective field theory, I can have these 4 fermion interactions. Again, here's quark, electron, electron, quark, but I can rotate this any way I want. So I know something about this for measurements at LEP and for measurements at the LHC. And again, it's this effective field theory thing where this guy is enhanced by a factor of energy squared over lambda squared relative to this guy. So it's because this guy is dimension 6, So it's got an energy squared upstairs, gets this enhancement relative to this guy. So when I look at this for the EIC, it happens exactly the same as in all these plots and tables I showed you. So here's two quarks making a Z. Okay, so I can have this modification of the Z vertex, and in the standard model of field theory, this modification is exactly the same as I wrote down for the LHC. So I've got some effective field theory couplings that can modify this coupling, and I've got a bunch of 4 fermion operators here that can come in. So you can do the same thing as I did in Higgs physics, as I did in LHC physics, and this is a paper that actually just came out a couple days ago from Raja at Argonne, doing this for the EIC, saying, well, how well can you do these fits at the EIC? And you can't read these numbers here, but I'll tell you the answers. So these are fits to tons of coefficients, and she nicely turned them into scales over lambda scale over square root of C. So if you think that the coefficients are 1, then you get a scale here. And she's done fits here for joint EIC, which means proton plus deuteron, and then fits for higher energy electron and proton colliders, compared with the kind of fits that we're getting from E plus E minus colliders and from Higgs physics, from diboson physics fits here. And if you look at these numbers, you see that some of these fits are about the same, but in order to improve on what we know now, you have to go beyond the EIC to higher energy to actually learn more from these fits. So I'm going to stop there and take questions. Okay, questions? Yeah.
The cross section from yesterday, which was glue to Higgs, no, Higgs to glue.
Does glue goes to Higgs?
Could you tell us how that shows that there is no fourth generation?
Oh, sure. Absolutely.
Thank you.
I have to write in the blackboard. Okay. Okay, so sigma glue goes to Higgs experimental. It's approximately sigma glue goes to Higgs theory, where I really mean PP. Okay, so right away when we discovered the Higgs, the cross section was sort of exactly what we predicted. Okay, so theory, sigma theory is equal to some alpha squared over v squared with some factors I don't care about. And then I take the top quark mass goes to infinity, and it's 4/3 squared. That's that form factor.
So F12.
Yeah.
Some over flavor.
Yeah, only the top quark matters because everything else couples proportional in mass. So this is the thing I call F1. So in the limit that the top quark mass goes to infinity, it goes to 4/3. Okay, so now suppose I had a 4th generation. So I'm going to have my 4th generation, which I'll call TB, since I'm not very creative. Okay, so the T is very heavy and the B is very heavy, and they're just copies of the standard model B. They just look like that. Okay, so what happens then is what I have is I've got a loop with a top quark. I got a loop with my heavy T, and I got a loop with my heavy B. Okay, so now my sum over quarks in the loops is 4/3 from the top plus 4/3 squared from the T plus 4/3 squared from the B. Okay, so now I add this all up and I get that instead of having this guy, I get this guy and whatever this number is, but it's a big number. It's much bigger than 2. And that's the answer, is that these guys just kill the Higgs cross section and they kill it by a lot. Yes.
And then those, but they have to, capital T, capital B, they have to be heavy.
Yes, absolutely heavy, because when I calculate this thing, there's actually dependence. If I make this just a fermion, Higgs, then it goes like M fermion squared log fermion over MH, if M fermion goes to 0 and it goes to 4/3, M fermion goes to infinity. So the argument only holds for heavy stuff. Yeah. But it was kind of amazing because before they found the Higgs, people were building these models with the 4th generation. And we said, well, we don't understand why there are 3 generations anyways. Why not 4 or 5? And bingo, we measured the Higgs and this did it. So what this says is that when people are building models, they'll talk about top quark, vector-like quarks, for example. They're not in doublets. They have to have different kinds of representations. So it limits what we're allowed to do severely.
We'll make models with like just a lighter 4th generation to try to evade this problem.
No, because if you had a lighter guy, it would show up in other ways. You know, this is a very specific Higgs argument, but if you had a lighter generation, it would show up in things like the rho parameter, for example, would rule that out. Okay. Questions? Yeah.
Couldn't it be that the 4th generation is too heavy so that the collider hadn't reached the threshold that we can?
No, because, and that's a really good question, because the Higgs couplings to fermions don't decouple because they go like the mass of their standard model like. Yeah. So no, this is literally and honestly the limit, the mass goes to infinity. It's the mass of the fermion over the mass of the Higgs. That goes to infinity. Yeah. So you can't get around it that way. The only way you can get around this kind of argument is by invalidating this, by making the new fermions have different SU2 representations in the standard model. And you can do it that way, and it's a lot of fun. Yeah, but you can't just copy it, fortunately. Okay. Anybody else?
It's a break. Go ahead.
I have one of these maybe very stupid questions. So I'm worrying about the why will you call this an effective theory? So like, for example, when we look at the 4 fermion theory, why it is effective is because that we ignore the Z boson there, right?
Right.
Yeah. But here it seems that we don't ignore anything.
But the picture is that we are ignoring stuff, that we're ignoring some really great new complete model that's happening at, say, 10 TeV or some high scale, that there's a model up there which has new particles like the Z. So it's got maybe a new Z prime, okay? But those new Z primes are too heavy to ever measure. So the picture is we've got this heavy stuff, and the only way we can see the footprints of this heavy stuff is by how it contributes to these coefficient functions. So it really is an effective field theory. We just don't know what's underlying it. And that's why we want to measure this stuff. So then we can try to play these games to fit what these coefficients are telling us. Yeah, it's a real effective field theory.